Alright, multivariate regression. Yeah, up to now, we've basically dealt with only one feature. Yeah, the size of the house versus the price. But machine learning has a lot of features, thousands of features. So we need a little bit of notation in order to represent a bigger set of features. The price of the house is still y, and y is still the label. The upper I is basically the number of training samples. We have 6 training samples, so you're gonna have 6 rows here. Yeah, we said we have m is 6 training samples. If you now look at one training sample, it has x1, x2, x3 features, and the superscript, denotes that it's the first training samples. In total we have d features, and in our case d is 3. Yeah. So the notation is going to change. Yeah. This is the notations we had for one feature. Now we have multiple features. Y predict will be w0 x0 plus w1 x1 plus w2 x2 plus all the way down to wd xd. Yeah. Now the first thing we're gonna do here is set x0 to 1. Yeah. So this will be 1. Yeah. And now let's define some vectors. So when there's a lot of features, that's where vectors come in. Linear algebra. Yeah. If you're not familiar with vectors, go and take a look at my math refresher on linear algebra. But for example, we can define a vector x. Yeah. And that's our feature vector. So it starts with 1, then we have x1 all the way down to xd, because we have d features. Yeah. The same we can do with parameters w. So we have a vector w equals from w0 all the way to wd. Okay. Now the size of this vector is, we have d plus 1 rows times 1 column. And this is the same, d plus 1 rows times 1 column. Now we can't multiply these because we have this issue, right? Remember, when you multiply matrices vectors, the number of columns of one vector need to be the same as the number of rows of the other vector. Yeah? So that's why we will generate W transpose. So we make from the rows, we make a row vector instead of a column vector. It's W0, W1, all the way to WD. Yeah. And now this vector is a 1 times d plus 1. Yeah. And now we can multiply this with the vector x. So if we multiply this with the vector x, is 1 x1 all the way down to xd. Yeah. And when we work this out, w0 times 1, we have w0 plus w1 x1 all the way down to wd xd. Yeah, so this vector product, and actually here I need to say is W transpose X. Yeah. Now remember, in the univariate case, the cost function C was equal to 1 over m, and then we take the sum from I is 1 to m of y predict I minus y I, and then we square, and the I gives you the sample number. Now in the multivariate case, what we do is we're just gonna put this term in here because this is the new y predict. Okay, so very simple, the cost function equals 1 over m, and then we have the sum of I is 1 to m of W transpose X minus yi. And then we square. And this is of course also for sample number I. Okay, so not too different from the univariate case. It's just that now we deal with vectors. W is the weight vector and X is the feature vector. Now let's look at the gradient descent update rule. Remember, in the univariate case, if we wanted to go to Wi plus 1, we took Wi and we subtracted alpha dc with respect to W in the point Wi. Okay? This is basically what this graph is saying. It's a man walking down the hill. But now we're dealing with more than one feature. Yeah? And remember, in the calculus refresher, we saw the Taylor series. And what does the Taylor series do? Well, Taylor series allows you to approximate a function by a polynomial near some point A. So we derive this formula. The polynomial equals f of A plus f prime of A times x minus A plus f double prime of A, x minus A squared, and I forgot here to divide by 2 faculty. This is what we saw last time. Now, in our case, the x is W0 plus delta W, and the A is W. Yeah? So if we go back there, this would become is the cost function in the point W plus delta W times the gradient of C in the point W. And then we have higher order terms, but we're not going to use them. So we're going to take the linear approximation, or the first order approximation of the Taylor series. And this is okay as long as delta W is small enough. We can approximate this curve by a straight line. Yeah? So if delta W is small enough, you will have a sort of straight line. Okay, so now what is this here? This is a dot product. This is a dot product that we've also seen in the linear algebra refresher. Yeah, the dot product, and a dot product gives a scalar. Yeah? We know that the outcome of a dot product of two vectors is a scalar. A scalar is just a number. And we've seen that it makes sense for delta W and the gradient of C to have opposite directions. Yeah? Because here is the derivative, the gradient is negative, whereas from W0 to W1 we go into the positive direction. So that means that delta W is proportional to minus the gradient of C. Yeah? So that would mean that delta W divided by gradient C equals a certain constant, proportionality constant, which is alpha. So this proportional relationship becomes an equality if we define a proportionality constant alpha. Okay, so that means that delta W equals minus alpha gradient of C in the point W. Yeah. So now what we're gonna do, we're gonna add W0 on both sides to the left hand side. Yeah. So we take W0 plus delta W equals W0 minus alpha gradient in W0. And the only thing we did was we added W0 on both sides. Now this here is W1. So W1 equals W0 minus alpha, and then the gradient in W, the gradient of C in W0. Okay? And that is my new update rule. So we have Wi plus 1 equals Wi minus alpha, and then we have the gradient of C in Wi. Yeah, so this is my update rule for gradient descent in the multivariate case. And you basically see it's very similar to the univariate case. It's just that we replace the derivative by the gradient.